All right, hello and welcome. In this example, we are going to look at how to calculate the total capacitive reactance in this circuit here. The first thing we need to do is determine our CT. Right? So CT, we are going to look at our relationship in this circuit, and from our voltage source's perspective, we see that we come up and have no choice but to travel through C1. So C1 is in series with whatever else is in the circuit. And as we continue on, we hit a node, so we'll open a parenthesis, we'll go down across C2, and that hits ground at the bottom here. And so that means C2 is in parallel with whatever else we have in the circuit, and that happens to be C3 all the way to ground, and so that means that C2 is in parallel with C3. Close that off, and then we will evaluate this innermost parenthesis working outward. So let's plug that into our calculator. We know that the parallel equation, we're just going to add those two together. Watch out for these because they need to be placed into the same notation here, so we can even write that out. We can say that our nanofarads here can move into picofarads. We can say that C3 is actually 250,000 picofarads, and we'll write that in instead for our C3 value. So we'll add those together. We'll say that we have 250,000 plus 100, and that gives us 250,100, and we'll take that in with our C1 value here. So we'll carry this on. CT is now equal to C1 in series with 251,000. Okay, so now we can do our C1 in series with 250,100, and that is our 1 over 1 over equation. So 1 over 1 over C1, 460, plus 1 over C2 and C3 in parallel with each other, or in series, in parallel with each other. So we'll add the 250,100 there, and that gives us our total capacitance, CT. And so that'll be 459, and that is in picofarad. Right? That's not our total reactance. That's not our capacitive reactance. Capacitive reactance is actually the resistance of our capacitors. So now that we've found our total capacitance, we can convert that into ohms. Right? So if you are working with Ohm's law, you need to make sure that your capacitors are actually in ohms. Otherwise, you are not working with Ohm's law. Right? So our Ohm's law allows us to flip this over, and we'll say that we actually have a new equation here that we're going to work with, and that is our XC, that's what our capacitive reactance is, we're calling it XC, is equal to 1 over, capacitors are always a little bit backwards, so that 1 over is that inversion that we're seeing there, 2 pi, that's our circle, our frequency, how fast we're moving around that circle, and then multiplied by our CT, the total capacitance that we have in the circuit. Right? So this goes all the way back to that unit circle again. So we'll plug in here. We'll say that XC is equal to 1 over 2 pi, our frequency, which we know over here is actually 2,200 hertz. So we can plug that in, multiplied by 2,200 hertz, multiplied by CT, which we know is 459 picofarads. So we'll plug that into our calculator, and that's going to be our answer. Send that out, and we'll say that we have 1 over 2 pi multiplied by our frequency of 2,200 multiplied by our small little capacitor value here, so it's going to be 459 times 10 to the negative 12. That gets us in pico there. So now we have a final answer here of XC is equal to 157,610. And we can move that into notation a little bit here. We can move it up by 3 and say that our XC is now equal to 157.6. We can even round that up there, 158 kiloohms. Right? It's in ohms now, which means we can apply Ohm's law. Let us know if you guys have any other questions.